Hello everybody, I hope all of you are doing well. So we were left with chapter 14, section 7 of Thomas Calculus, which is talking about extreme values and saddle point. First, as usual, I'll be talking about what we have studied in Calculus 1, which is talking about two variables. We there had only x and y variables, independent and dependent variables. So we were working on two-dimensional space. So first, let me give you a backup of what you have studied in Cal 1 for extreme values, and then I will come into the subject of extreme values and saddle point that we have got for several variables in here. So when we were talking about extreme values in calculus, extreme values included what? Included maximum and minimum points. Okay, so we had max and min points. Where were these max and min points happening? They were happening at the critical numbers. Okay, so if we had a function, for example, f of x, that's equal to, let's say, x squared plus x, what were we doing? We were first finding the critical numbers of this function. How were we finding critical numbers? If you remember from Cal 1, the definition of critical numbers was that the first derivative of the function must have equal to 0 or undefined. So we were first finding the first derivative of the function, equalizing it to 0. Okay, then we were having values for x. Okay, and then those values of x that we were finding, we were determining whether they were max points, min points, or none of them. We had local max, local min, and global max and global min. So this was the way of finding extreme values, that means local maximum and local minimum, when we were working on two-dimensional space. When we are coming to several variables, generally here we are talking about three-dimensional space where z is equal to a function of x and y. That means we have got f of xy. We will be talking about extreme values, which is local maximum and local minimum. Okay. And we will be also talking about saddle point, which is something, a new idea, new concept that we have got here in three-dimensional space, but we do not have this kind of point in two-dimensional space when we have got x and y. So what is local maximum? Of course, the definitions are mostly, let me say, the same as what you have studied in Calculus 1. We say first, as the definition of local extreme values, we have got the function f of xy, which is defined on a region and containing the point a and b. So a and b is in the domain of the function f of xy. F of ab, so when we put that ab into the function f of xy, this ab, this value of the function, will be called a local maximum if this value of f is greater than or equal to every other value in the domain of the function. And this f, a, and b, that means when we put a and b in the function that we have got, it is a local minimum if the value of that function at that point is less than or equal to every other value that is in the domain of the function that is given to us. So the definition is pretty much the same thing that you have studied in Cal 1. And these maximum and minimum points are called relative extrema. Local extrema or relative extrema. Here, this figure that we have got here, it's showing local max points. Here, the point that we have got is max. Okay, why? Because in that domain, it is the highest point, and higher, this is like, let me say, the maximum point, and every value else is less than that point that is given. This point, the same thing, it's max, and it is more than every other value that is in that domain of the function. And this one is minimum because it is the smallest value in that region, in that area that we have got for the function. This is in pictures. Okay, let's see what's the first derivative test for local extreme values. So if we have got f of xy that has got if f of xy has got a local maximum or minimum value at an intermediate point of AB, then the first partial derivatives exist. So if you know that a function has got a local maximum and local minimum at a specific point AB, that means their first partial derivatives exist. And at that point where local max and local min exist, the values of the functions, the first derivative of the functions is equal to 0. That means f sub x and f sub y are equal to 0. Okay. We are coming to the definition of critical numbers or critical point, let's say. What is a critical point? The critical point that we are defining here is nothing more than what you have studied in Cal 1. So an interior point of the domain of the function. So we have got a point in the domain of the function f of xy, and we know that f sub x and f sub y exist. They must both exist. If f sub x and f sub y we find values that are equal to 0 or does not exist, that means undefined, then these points that we have got are called critical points for that function. So the definition is the same of critical numbers, critical points, is the same thing as you have studied in Cal 1. It happens at the first derivative of the function where the first derivative of the function is either undefined or is equal to 0. Okay, we have got a new concept here that's called the saddle point. That saddle point does not exist in Cal 1 because it happens when we have got three-dimensional space. What is that saddle point? Simply talking about saddle points, when we have got a function that is differentiable and it has got critical points, at that critical point, the point that we have got, that means f of AB, it is less than other points that are in the domain, and it is at the same time more than the other points that are in the same domain of the function. So for example, if you imagine it, if I put two cups on each other, okay, so I'm putting, let me say this one, let me say two cones on each other, okay, and I connect those two cones to each other and put them on each other. That point in here, okay, that point that is in here, it is local minimum for those points that are in here, and it is local maximum for those points that are here. So this point that is given in here, this one, is min and also it's a max point at the same time. So when we have got a point that is maximum and minimum at the same time, that's called a saddle point for the function that is given to us. Here, the first example is given to us, and it's showing how a point is a local maximum and a local minimum, like let me say verbally, like imagining the function that we have got, imagining the domain of the function, imagining the range of the function. But before going to solve these examples by imagining the points, we will go through the steps of finding critical numbers, local maximum and local minimum points, and then we will come back to solve example 1 and example 2 to find their extreme values and saddle point. Okay, so here is the test for finding maximum, minimum and saddle points. What does the test say? We have got this theorem. It says we are using the second derivative test for finding local extreme values. So that test mentions that, exposes that we have got the function f of xy that is given to you, and it is first and second partial derivatives are continuous. So we have got a function, its first and second partial derivatives exist and it is continuous. And we have got f sub x for AB, f sub y for AB is equal to 0. That means we are equalizing the first derivative of the function, the first partial derivative of the function, to 0. Then f has a local maximum, okay, so it has got a maximum point at AB at that point, if we know that f sub xx is less than 0 and f sub xx, f sub yy minus f sub xy to the power of 2 is greater than 0. So having those two conditions here, this condition and that condition gives me what? Gives me a local maximum point. However, if the condition is like that, f sub xx is greater than 0, but the discriminant is greater than 0, and and the discriminant is greater than 0, it is giving me a local minimum point. Okay, so the discriminant is the same if you look at those two ones. Okay, their discriminants are both greater than 0, but their second derivatives with respect to x, if it is less than 0, it is maximum point. If it is greater than 0, it is a minimum point. Okay, how about a saddle point? For seeing whether it's a saddle point or not, the difference is in the discriminant. If f sub xx, f sub yy minus this expression square, if it is less than 0, then we will have a saddle point at the point AB. If this discriminant is less than 0, if it is equal to 0, sorry for that, then we say that the test is inconclusive. What does that mean? That means we cannot use this test for finding maximum, minimum, or saddle point, and we are leaving this test. We cannot use it for checking the local extreme values of that function. And here in the section, no other methods are mentioned for finding extreme values when the test is inconclusive. So we will, in case when you have got this expression that is equal to 0, you just leave the question and you say that the test is inconclusive and we cannot find the local extreme values using that method. Okay, that thingy, f sub xx, f sub yy minus f sub xy squared, that's called a discriminant. Okay, so here is the test for finding local extreme values in the saddle point. So I'm coming back to the example that we had first. What does it say? It says find local extreme values, that means maximum, minimum, and saddle point, for the function that is given to us, which is equal to x squared plus y squared minus 4y plus 9. What we will be doing here, we will be finding the critical numbers and check whether they are maximum points, minimum points, or saddle, or the test is inconclusive. Okay, let's start. So first, the function is given to us. We have to find f sub x and f sub y to find the critical numbers. So what is f sub x? You know, it's the first partial derivative of the function with respect to x, and we consider every y is a constant. So here f sub x is equal to 2x. This part will equal to, the y square will equal to 0, minus 4y is 0, and plus 9 is also 0. So f sub x is equal to 2x. F sub y is equal to what? F sub y, we consider x's are constants. So x squared, the derivative with respect to y is 0. Y squared, the derivative of it is 2y. And we have got minus 4 plus 9 is equal to 0. What do we have to do? Since we have found the first derivative of the function, for finding critical numbers, we have to check whether the first derivatives are equal to 0, or we have got x's and y's that makes the functions, the first derivative functions, undefined. Here we do not have anything that makes the first partial derivatives undefined, so I'm simply equalizing these expressions equal to 0. F sub x equal to 0, f sub y equal to 0. What do I get from this one? I get 2x is equal to 0. That means x is equal to 0. And from here, I get 2y minus 4 is equal to 0, from which I get x is equal to, that becomes 4 over 2, and that's equal to 2. Sorry, that's not x, I mean y. Okay, so what do I have? I have got x and y. When I solve the first derivative of the function, I get the values of x and y. Okay, so here I have got the point AB. Okay, that's the x and y. It is equal to 0 and 2. That's what? That's the A and B that we were talking about. the value of the function. Okay, so we have found the critical number that's equal to 0 and 2. That is the critical number. To check whether that critical number is max, min, or a saddle point, or the test is inconclusive for this one, we have to check these conditions that are given in here. For checking these conditions, what do we need? We need the second derivatives, f sub xx, f sub yy, and f sub xy. So let's find them. So first we are finding f sub xx. F sub x. So the derivative of the first f sub x with respect to x. The derivative of that 2x that we have got here is what? It is 2. We also have to find f sub yy. That means the derivative of f sub y with respect to y. The derivative of this one is also 2. Okay. We also need what? We need f sub xy for checking the test. F sub xy or yx, it doesn't matter because we have studied previously. When the function that we have got is continuous, f sub xy is equal to f sub yx. So finding either of them doesn't make a difference. Okay, so finding the derivative of this one with respect to y, that's equal to 0. Tamam? Okay, now we will come and check the definition that we have got here, or let me say the test that we have got here. According to what we have got, I have to check the first one. Okay, we know that f sub xx, that's equal to 2, and it is less than 0. So this part is satisfied. Okay, now let's check if the discriminant satisfies this one or not. So what do we have for the discriminant? The discriminant, it says that f sub xx multiplied to f sub yy minus f sub xy squared. Let's see what is it equal to. F sub xx is equal to 2. F sub yy is equal to 2 minus f sub xy squared, that is 0 squared, because f sub xy is equal to 0. So that's equal to 0. What is the value of this one? The value of this one is equal to 4, which is what? Which is a number that is greater than 0. So it satisfies what? This condition that we have got here. Since if you see that the discriminant, since you see that the discriminant is greater than 0, and f sub xx, which is equal to 2, and it's less than, sorry, if 2 is greater than 0, I do not know why I have written that's less than 0. That is greater than 0. Sorry for that mistake. Okay, since f sub xx is equal to 2 and that is greater than 0, that means it is this one, and f sub xx, f sub yy, that means the discriminant in total is greater than 0. So we have got both of them, both of the conditions satisfied. So we say that, okay, so the critical number that we have got 0, 2 is what? Is local minimum. Okay, so that's how we are using this test for checking whether a critical number is a local max, local min, or a saddle point.